The sinc function is defined piecewise for real x as follows. If x is not equal to 0, then sinc x equals sin x over x, and if x equals 0, then sinc x equals 1. Part A. Explain why a piecewise definition for this function is necessary, and by considering an approximation for sin x when x is close to 0, or otherwise, explain why the definition of sinc 0 is appropriate. We can note that if x equals 0, then sin x over x is sin 0 over 0, which is 0 over 0, which is an undefined quantity. And so we can't use the formula sin x over x to define sinc 0. On the other hand, for all x not equal to 0, sin x over x is well defined, i.e. we can plug non-zero x into that formula and get a number out of it. And so we can see that the domain of sin x over x is r minus 0. And the set notation shown in the blue box is set subtraction. That creates a set which contains everything in R except 0. And graphically, that set looks like the number line, the set of all real numbers with 0 removed. And so if we want to define sinc x for all real x, then sinc 0 simply cannot be based on the formula sin x over x because its value is undefined at that point. And so we are forced to make a separate definition for sinc 0, and that means that the definition of the function must be piecewise, i.e. it can't be defined using a single formula. And now we must explain why the specific definition of sinc 0 equals 1, is appropriate. And the question suggests that we do that by considering an approximation for sin x when x is close to 0. Well, there's a well-known approximation for sin x, and that is that if x is close to 0, then sin x is close to x, as long as x is measured in radians. And that is usually called the small angle approximation. And this approximation becomes more accurate as x gets smaller, i.e. as x tends to 0. And so we have that if x is close to 0, then sin x is close to x, so that sin x over x is close to 1. And this is an approximation that becomes better as x gets smaller, as x gets closer to 0. And so we can say that the limit as x tends to 0 of sin x over x equals 1. And in fact that result, that the limit as x tends to 0 of sin x over x equals 1, can be proven by a purely geometrical argument involving no calculus. However, we haven't been asked to prove this result in this question, so I'm not going to do so here. We can look at the graphs of x and sin x shown here to see that the result does indeed seem to be true. We can see that the graphs of x and sin x do indeed converge as x tends towards 0. And in fact, this graph suggests a couple of other properties of sin x over x. And note that we are considering x lying between 0 and pi. For x in this range, we can see that sin x is less than x, so that sin x over x is less than 1 for x lying between 0 and pi. In addition, we can see from the graph that if x sub 0 is less than x sub 1, then sin x sub 0 over x sub 0 is greater than sin x sub 1 over x sub 1. So if we look at this particular value of x sub 0 and this particular value of x sub 1, then the blue line indicates sin x sub 0, the grey line indicates x sub 0, the green line indicates sin x sub 1, the purple line indicates x sub 1. And we can see that the ratio of the blue line to the grey line is greater than the ratio of the green line to the purple line. So that for these two values of x sub 0 and x sub 1, then the stated result is true. And from the relative sizes of sine x and x for all values of x between 0 and pi, the graph suggests that this result is true as long as x sub 0 is less than x sub 1, i.e. it suggests that sine x over x is a decreasing function in this range. And so by using those facts, we can see that the graph of sine x over x will look like this near x equals 0, i.e. it will be undefined at x equals 0, it will get closer and closer to 1 as x tends to 0, and the graph will lie below y equals 1, with that final fact being true because sine x over x is a decreasing function in this range. And it's worthwhile noting as well that the graph will be symmetrical about the line x equals 0, i.e. about the y-axis. And that follows because under a reflection in the y-axis, x goes to minus x, so sine x over x goes to sine minus x over minus x, which equals minus sine x over minus x, which equals sine x over x. So the value of the function is unchanged for any x when reflected in the y-axis. And now we come to the main point. If we choose sinc 0 equals 1, then we can fill in the hole at x equals 0, and we obtain a graph like this, where we have replaced the hole with the value sinc 0 equals 1. And that is nice because now the graph is what we call continuous at every point. It has no breaks or jumps. And indeed, if we chose any other value for sinc 0 other than 1, then the function would not be continuous at x equals 0. Generally, we want functions to be continuous. They are nice functions. Specifically, if a function is not continuous at a point, then we can't differentiate it at that point. And now, with this definition of sinc 0 equals 1, then the function sinc x is continuous everywhere and also differentiable everywhere, i.e. we can assign it a gradient at every point. And although there is a formal mathematical definition for a continuous function, for our purposes this one will suffice. A continuous function is one whose graph can be drawn without lifting a pencil from the page at any point. We can also note that with the definition sinc 0 equals 1, we have a turning point at x equals 0, and that's because we know that the sinc function is decreasing between 0 and pi, and so by symmetry, sinc 0 equals 1 is the local maximum. And because sinc x is decreasing for x between 0 and pi, its graph will look something like this. However, we can't yet tell exactly what the shape is going to be, and at the moment we don't know where or indeed if it will cross the x-axis. But we can be sure that there will be no other local maxima in that region, i.e. no other turning points between 0 and pi. Part B. By considering the graphs of y equals sine x and y equals 1 over x, sketch a graph of y equals sinc x for x in the range minus 7 pi by 2 to 7 pi by 2. And here for reference are the two graphs in the relevant range. And here also for reference are the two parts of the definition for sinc x. Now, in order to sketch a graph, we have to identify its key features. So, for example, we have to identify its zeros, where it crosses the x-axis, its turning points, where its gradient is equal to 0, its asymptotes. We have to decide if the graph is continuous or discontinuous at any point, if it is even, odd, or neither as a function, and whether or not it is periodic or has any other obvious special features of interest. Now, we have already noted that the function is even, and that's important because we need only plot it for x greater than or equal to 0, and then reflect the graph in the y-axis to generate the negative portion. And so that will save us a lot of effort. Now we can note that we have to multiply the y values of the two functions 1 over x and sine x to generate the graph of sinc x for x not equal to 0. And that immediately tells us that the graph of sinc x must be continuous for x not equal to 0, and that's because a product of continuous functions is continuous. And that tells us that for x not equal to 0, the graph of the function will have no breaks or jumps. Now, the sketching of the sinc function is quite a common university interview question, and I will approach the problem in that spirit. And so I will use mainly intuitive arguments with little or no calculus and no use of calculators. Here, for reference, we repeat the two parts of the definition of sinc x, and we recall that we are only considering the definition for x greater than 0. We first consider the zeros of the function, and these occur when either 1 over x or sine x are 0. And that's because 1 over x times sine x equals 0 means that either 1 over x equals 0 or sine x equals 0. But since x is greater than 0, then 1 over x is greater than 0. And so we get no zeros due to 1 over x, and that's because the equation 1 over x equals 0 has no solutions for x greater than 0. On the other hand, if x is greater than 0, then sine x equals 0 when x is pi or 2 pi or 3 pi, and so on. In other words, when x equals n pi, where n is an integer. And so this tells us that sinc x crosses the x-axis at the same places as sine x. We now consider the turning points, and in fact we are just going to try and get a rough idea of where they occur. Now we know that the turning points of sine x occur at 3 pi by 2, 5 pi by 2, 7 pi by 2, and so on, which we can write more concisely as n plus 1/2 pi for integer n. And we can locate the turning points of sinc x by considering what happens to the turning points of sine x when we multiply the two functions being 1 over x and sine x. And here we have representative portions of the 1 over x curve and sine x curve near a turning point. And please note that these graphs are not to scale. This point on the left is a 0 of both sine x and sinc x, and so is this point on the right. And we should further note that sine x is symmetrical about its turning point, whereas 1 over x is not symmetrical about that turning point. And in fact, 1 over x is higher to the left side of the turning point and lower to the right side of the turning point. Now consider the turning point of sine x. When we multiply by 1 over x, it will be mapped to some lower point, like so. Now consider 2 points located symmetrically on either side of the turning point. Now when we multiply by 1 over x, the left-hand point will be mapped to a higher location than the right-hand point, like so. And that will be true for any pair of points that are initially symmetrical about the turning point. And if we join the dots, we get an approximation to sine x over x in this range, from which we can see that sine x over x is steeper on the left-hand side and shallower on the right-hand side. And since the left-hand side of the function is steeper, it reaches its turning point earlier, i.e. the turning point shifts left relative to that of sine x. And we will say that the nth turning point shifts left by an amount epsilon sub n. And we should note that the same argument works for a negative turning point of sine x. And so the turning points of sine x over x will occur at n plus 1/2 pi minus epsilon sub n, where epsilon sub n is some small quantity. So the question is, can we say anything more about it? And we can note that the reason for the shift in the turning points is that sine x is symmetrical about its turning points, but 1 over x is asymmetrical about the same points, so their product is also asymmetrical, i.e. it is the asymmetry of 1 over x about the turning points which causes the shift. But this asymmetry decreases as x increases, as we can see if we look at the graphs of 1 over x near the first 3 turning points of sine x. And since the asymmetry in 1 over x decreases as x tends to infinity, so we expect epsilon sub n to tend to 0 as x tends to infinity. That is, we expect the graphs of sine x over x near the turning points to look like this, with epsilon sub 1 being the largest shift and epsilon sub 3 being the smallest. And of course, we would like to know more about the turning points of Sinc X. We would like to be able to at least estimate them, and we will estimate the location of the turning point for epsilon sub 1, and we know that the other epsilons are smaller, and because we only want to sketch the function, this will be sufficient. And we do this estimation by approximating the symmetrical part of the sine function with a symmetrical pair of straight lines. And so we approximate this part of sine x with these red and blue lines. But of course, we are only interested in the approximation for y lying between -1 and 0. And of course, we want to know where this point, the turning point of sine x, which is represented by this point in the approximation, moves to when we divide by x. It's easy to show that the blue line has equation y equals -2 over pi times x minus pi, and I'll call that L sub b, and that the red line has equation y equals 2 over pi times x minus 2 pi, and I'll call that L sub r. So for y between -1 and 0, we approximate sine x as the union of L sub b and L sub r. Of course, we want an approximation for sine x over x, which in this case is LB over x unioned with LR over x. Of course, 1 over x is not constant in this range, and so we make 2 further approximations. On the left side of the turning point, we approximate 1 over x by its value at the midpoint, where it takes the value 4 over 5 pi. And similarly for the right side, we approximate it by its midpoint with the value 4 over 7 pi. And with those further approximations, we have the approximation for sine x over x, which is 4 over 5 pi times LB, unioned with 4 over 7 pi times LR. Graphically, the approximation for sine x over x is shown here, with associated equations as shown. We see that the approximate turning point t of Sinc x is the intersection of L sub b and L sub r. And because we have a linear approximation for sine x over x, we can solve L prime sub r and L prime sub b as simultaneous equations to obtain the coordinates of the turning point. And if we do so, we find that t has coordinates 17 pi by 12, -2 over 3 pi. We want the value of epsilon sub 1, the shift of the turning point, which we show here on the graph, with the dotted line indicating x equals 17 pi by 12. And we see that with our approximation, epsilon sub 1 is pi by 12. We can also note that -2 over 3 pi is in fact sinc of 3 pi by 2, i.e. it is the y-coordinate of this point. Now, we haven't made approximations for epsilon sub 2 or epsilon sub 3, but we know that they will be smaller than epsilon sub 1, and thus we approximate the turning point for epsilon sub 2 as follows: 5 pi by 2 minus epsilon sub 2, 2 over 5 pi, and for epsilon sub 3 as follows: 7 pi by 2 minus epsilon sub 3, -2 over 7 pi. where we are assuming that the y-coordinates of the turning points do not shift much from the corresponding values of the sinc function. We now consider the asymptotes, and the question here roughly is, does the function approximate a straight line more and more closely as it recedes from the origin? A function can have three types of asymptote, each of which is defined in terms of a limit expression. So a function can have a horizontal asymptote, which is defined like so. A function can have an oblique asymptote, where it approaches the line y equals mx plus c, and can be defined formally using this expression. And a function can have a vertical asymptote, which is defined using this expression. And we should note in passing that a function can cross an asymptote even infinitely many times. And here we see an example of a function with an oblique asymptote of y equals 2x plus 1, and the function crosses that line more than once. Now we can easily show that sinc x has a horizontal asymptote of 0, i.e. of the x-axis. That is, we can show that the limit as x tends to infinity of sinc x equals 0. Now, the definition of sinc x for x greater than 0 is sin x times 1 over x, and we know that sin x lies between -1 and 1, and that 1 over x tends to 0 as x tends to infinity. And thus we must have that sinc x tends to 0 as x tends to infinity, as we can show formally. Now note that the statement sin x lies between -1 and 1 can be rewritten as mod sin x is less than or equal to 1. And now, for x greater than 0, mod sin x over x becomes mod sin x times mod 1 over x, which equals mod sin x times 1 over x, because mod 1 over x equals 1 over x for x greater than 0. And now we can write that mod sin x times 1 over x is less than or equal to 1 over x because of this fact. And we know that 1 over x tends to 0 as x tends to infinity, and hence so does mod sin x over x for x greater than 0. In other words, the limit as x tends to infinity of sinc x, which equals the limit as x tends to infinity of sin x over x, equals 0. And this immediately tells us that sinc x can't have any oblique asymptotes, i.e. it can't end up tending towards some other straight line, and that's because limits are unique. A function cannot simultaneously tend to two different limits. We still have to consider the possibility of vertical asymptotes, however, and these occur where the function tends to either positive or negative infinity at some finite value of x. Now, when x is greater than 0, both sin x and 1 over x are finite, so there can be no vertical asymptotes when x is greater than 0. On the other hand, 1 over x tends to infinity as x tends to 0, so potentially sinc x could have a vertical asymptote there. But in fact, in part A, we have already seen that sin x over x tends to 1 as x tends to 0, so sinc x has no vertical asymptotes. We now ask, is the function periodic, or does it have any other special features? So first, is sinc x periodic? The answer to that question is no. Now, a function is periodic if its graph remains unchanged when we translate it along the x-axis by some displacement. For example, sin x is periodic because if we translate it by pi in either direction, we get the same graph. However, we know that the turning points of sinc x are shifted from n plus 1/2 pi by gradually decreasing displacements. So if we shift the first turning point onto the second turning point won't be shifted onto the third turning point. And so we will produce a different graph by that shift. And thus sinc x is not periodic. Does SyncX have any other special features? Well, this is a fairly open question, but there is one particular feature that we can examine. We saw earlier that mod sin x over x is less than or equal to 1 over x, but in fact we can have the equality there. We can have mod sin x over x equals 1 over x. And that's interesting because it tells us that the graph of the sinc function meets that of 1 over x. And 1 over x is easy to compute, of course, so it gives us a way to find some other values of the sinc function without a great deal of work. Now, if mod sin x over x equals 1 over x, then we get two equations, sin x over x equals 1 over x, and sin x over x equals negative 1 over x. And we can solve both of those equations trivially. Mod sin x over x equals 1 over x for x greater than 0 tells us that sin x equals 1, so that x is pi by 2 or 5 pi by 2 or 9 pi by 2, and so on. And these define points of tangency between sinc x and 1 over x. And similarly for the other equation, we find that sin x is negative 1, so that x is 3 pi by 2, 7 pi by 2, 11 pi by 2, and so on. And these define points of tangency between sinc x and negative 1 over x. And so from that we have that sinc pi by 2 equals 2 over pi, sinc 3 pi by 2 equals negative 2 over 3 pi, sinc 5 pi by 2 equals 2 over 5 pi, and sinc 7 pi by 2 equals negative 2 over 7 pi, and so on. And in the spirit of the question, I shall work out rough values for these without a calculator. And first we note that pi is approximately 22 over 7, so that 1 over pi is approximately 7 over 22. And by long division, we find that 7 over 22 is approximately 0.318 or 0.32, which for our purposes is close enough because we only want to sketch the graph. And from that, we have the following approximations. 2 over pi is 0.64, negative 2 over 3 pi is negative 0.21, 2 over 5 pi is 0.13, and negative 2 over 7 pi is negative 0.09. Now, when sketching a function, it's always worth computing any nice, easy values, if you can find some. And because sinc x is defined in terms of the sine function, the obvious values to investigate are the multiples of pi by 4, as shown here. Now first we note that sine pi by 4 equals root 2 over 2, which has the well-known value 0.707, with that value being well known at least to people who have studied some electrical theory. And by the symmetries of the sine function, the other quantities shown in green also have the same value. And also by symmetries of the sine function, the quantities shown in yellow have the value negative 0.707. And so we have that sinc pi by 4, which is sine pi by 4 over pi by 4, becomes 4 over pi times 0.707, and 4 over pi is twice 2 over pi, which becomes 1.28, and that multiplies out to give us that sinc pi by 4 is approximately 0.9. And in fact, by calculator, sinc pi by 4 is 0.9003 to 4 decimal places, so this is a pretty accurate result. And now, using elementary arithmetic, we can calculate the following nice values. And now all that is left to do is to sketch the information that we have gathered in the requested range, and we shall do so with no further commentary. And finally, here for comparison are the computer-generated graphs of y equals sinc x, y equals 1 over x, and y equals minus 1 over x over the requested range.